you do this the same way you did the other ones, right? Differentiate both sides of this, implicitly find dy dx. Derivative of secant is secant y tan y, but then you need to multiply by that because it's y, not x. You isolate dy dx. You get 1 over secant y tan y. You need a few identities from, or you need at least one identity here from grade 12 math. 1 plus tan squared is secant squared. So you could change this around so that tan y is square root of secant squared y minus 1. We don't know that it's always positive or anything yet, so that's why I'm leaving this plus or minus in. Before we used something and we said we're just going to do the positive because we know it's by looking at the graph it's always positive. So if you replace secant of y with x, because that's what you originally started with, and you replace tan y with that expression and the plus or minus, which is actually that, because secant can become, okay, because secant can become this. Secant becomes x, right? You end up with an expression that looks like this. Now, I don't expect this to be obvious algebraically here, because you kind of have to think about it when you do this. If you look at the graph, people don't like this plus or minus thing here. If you look at the graph, instead of having sometimes it's positive this, sometimes it's negative this, if you look at the graph of the thing, which hopefully this will open up here, this isn't on a page anywhere. We looked at it at the end last time. If you look at the graph of this thing, the slope is always positive for arc secant. That is not arc secant. That is secant, which I obviously didn't take away, right? This is a reflection over y equals x of part of it, right? Remember that the inverse, right? This is the secant graph, those U-shaped things. This is the portion of it that goes from 0 to 180, right? You couldn't do the portion that goes from negative 90 to 90 or negative pi over 2 to pi over 2 because it wouldn't be a function. It would go like this, right? And we don't want that. I don't know if I did it so it traces this, right? That's it, right? This is the inverse of that part. And if I was to continue over here, it's going to make it so it's not a function. So if we're going to write it as a function, we don't want that. We want the part that continues on here. So you want this part, and you want to keep going down to here, right? So it just draws that part, the part from 0 to 180. So that's what the arc secant function looks like, inverse secant. The slope is always positive if you look at it. Every portion of that graph, the slope is always positive. When x is, if you know that fact, then we kind of get around this pretty quickly. If you looked at this and said when x is positive, when x is a positive number, it must be plus this, right? And when x is a negative number, it must be minus this. Because if you have x as a negative number and there's a negative out here, it turns out positive. And if x is a positive number and this is plus, it turns out positive. If it's always going to be positive, we can just say absolute value of x, and you get the slope that way. You don't have to worry that much about, I don't think it's going to be critical to the understanding in this course to see where that comes from, but it isn't just, arbitrary. The absolute value, all it means is ignore the plus or minus because it's always positive. When it's negative, the x will be negative, so they'll cancel out anyways. Okay? So that is that. That's probably, all we're going to do with inverse trig functions. We're going to look at 3.9, the exponential and log functions. Okay?